Okay, so welcome everyone to the first meeting of the Culture Seminar online this semester. It's my pleasure to introduce our first speaker, Elisenda Feliu from University of Copenhagen. She will talk about parametric polynomial systems and biochemical networks. Elisenda, please.
Thanks, Cliff, for inviting me and all the organizers. I'm very happy to be in New York. I've never been in New York, but finally I'm in New York somehow. But yes, so today I will talk about some systems of polynomial equations that appear when modeling biochemical reaction networks. And I will focus mainly on tools to study them. So that's the goal of today. And let me start with here it is, just a brief introduction of what the talk is about, right? And the talk is about understanding systems that have this form here. I hope you can see the mouse when I move it. And these systems of polynomial equations, they are formed of two types of equations. The first is you have these polynomials of any degree, and the coefficients, you have some parameters in the coefficients, but with the particularity that you fix the sign of the coefficients and you might fix some relations among the coefficients. For example, here you see that K2 is repeated in here, and here the K3 is repeated in here. And I say we fix the sign, and by that I mean that the K's are positive. So the sign is encoded only in front of the parameter. So this is the first set of equations, and the second set of equations are just defining an affine linear variety. So you have to imagine the first equation, set of equations define an algebraic variety, typically nonlinear, and then you have these affine linear varieties that intersect, and you cut the solution set of the original variety, and you want to study what happens when you vary the case, so the coefficients of the variety, and the level set of this affine linear space. And all this, you want to understand what happens with the positive solutions, not any solutions. So this is the setting, right? And so a picture for the setting, it's not corresponding to these equations because here I have 4 variables. So this is another set of equations, but you can see we have to think that we have this family of algebraic varieties that vary when you vary the coefficients, the case, and then you intersect them with these parallel translates of a vector space. And you see, you look at the intersection. So here in the first figure, every time I take a red line and a dashed blue line, I will always get 1 point. So this is telling me that for any choice of parameter values, this corresponding system has one solution, always positive solution in the positive order. For the second set of equations that gave rise to this figure, you can see there are some parameter values that the intersection also consists of 1 point. For example, here, this curve, whenever I take a blue line, I only get 1 point. But here below, I have a red curve that intersected with one of these blue lines, gives me 3 points. So in this case, the number of solutions of my system depends on the parameter values. So what are the questions we are interested in understanding? Well, for this talk today, the question is about counting, and especially counting whether and when this solution set have at least 2 elements. This is a property that I call multistationarity because it comes from this application setting. And I will say a bit more about where the systems come from in a short while. But essentially, the talk is about understanding whether I can pick K and C such that this set has at least 2 elements. In the first figure I showed you, we could not. And in the second figure I show you, we could. If that's true, then we want to go a bit deeper and understand where that happens. And another property I want to talk about today is about whether the parameter region where this happens, where multistationarity happens, is connected. And of course, all these questions, in principle, there are algorithms you can apply from semi-algebraic geometry, quantifier elimination, where you put the problem into the system and you might get an answer. But here, the main difficulty we encounter is that the systems of interest have a lot of parameters and a lot of variables. And usually you cannot really use these generic algorithms. You need to put in some more information about particularities of your system. So the plan for the talk is to say a bit where the system comes from, to motivate the questions. And then I will cover two topics. The one is the parameter regions of multistationarity. This is some older work, but it kind of has the ingredients that I need to talk in part 2, where I will talk about the connectivity, which is very recent work with Mate Telek. Yeah. Of course, if you have questions, just interrupt me and anything. I will be happy to clarify if there is something I'm going too fast over or whatever. So where does the system come from? And here you get the summary in one slide, and I will go through it. So for the setting is that we are trying to model what happens with concentrations of some chemical species or biochemical species or animals, any entity that, or any group of entities that are related through reactions that make them change. So here you can see we will have, if I have one unit of X1, then it gets transformed into X2. Here we will have when X1 and X2 meet, we will get two entities of X2. And this type of representations occur in chemistry, that's the standard one. Also in biochemistry, when these X's are proteins, for example, or RNA molecules. It can also be animals. There are many models of animal interaction that can be expressed as a reaction network at the background. And also these famous SEER models, many of them, they also can be represented like this, where X1, for example, is susceptible people, and and X2 could be infected people. Not like this reaction, right, would correspond to that. And when you have set up your system of how these different entities interact, then you would like to model how the network affects the concentration or the abundances of each of them. And here today, I'm in the chemical setting where an assumption that is often made is that of mass action, it's called, that you assume somehow that everything is well stirred, homogeneous, and the entities just meet randomly. And when you do that, it's justified to model these concentrations with a system of ordinary differential equations, which is essentially given by first deciding how fast each of the reactions occurs. And how fast it occurs depends on how much of the reactant there is, like the multiplicative version. So here, for this reaction, it depends on X1. For the second reaction, it depends on X2 squared, because we need 2 molecules of X2 to occur, and the same for the third. And then the rate is assumed to be proportional to this, right, to these abundances. And when you have the rate for each reaction, then you look at how much each reaction contributes to the net production of each of these species. And here you can see in this matrix, the first row encodes how much of X1 is produced or consumed when each reaction occurs. So when the first reaction occurs, I'm consuming 1 molecule of X1. Now I say molecules because I think in the biochemical setting. When the second reaction occurs, 2 molecules of X1 are created. So that's where the 2 comes from. And when the third reaction occurs, 1 molecule of X1 is consumed, right? So that's the -1. And you do the same for X2. In that way, when you make the product, you will get the sum of the velocities of each of the reactions weighted with the net production of the species in the reaction. So this is the system that we want to understand. And in general, you can always write it as a matrix N, which encodes the production of the species in the reactions, and this vector of monomials coming from the reactants, which is multiplied with this constant that is called the reaction rate constant. And this reaction rate constant is positive. And these are the case I had in the first slide today. So this is the system we want to understand. And of course, here you want to understand everything about the system. You want to understand whether there are periodic solutions, what happens with the solutions, are they bounded, not bounded, etc. But a very first basic observation is to see that all the derivatives of the trajectories belong to the image of n. So in other words, you can say that if I have a left vector, a vector in the left kernel of n, right, will give me a relation on x dot equal to 0, right? So if I have a w, such that w times n is 0, then w times x dot is 0. So w times x is constant along trajectories. So this ODE system typically is not full dimensional. There are typically these linear affine spaces where the trajectories are confined to, and they are found by simply finding a basis of the left kernel of n, right? And these are the equations I had in the beginning with the blue C's, right? So these are where these equations come from. And for today, I will look at the steady states, that is the points where x dot is 0, right? And that means that this polynomial system here, this polynomial that needs to be 0, and the equations that constrain the trajectories need to be satisfied. And when I vary the kappas and when I vary the c, I have a family of polynomial systems, and I'm looking for the solutions of them in the positive ortho, because now you see why, right? Because we are looking at abundances, at concentrations. So we are interested in positive values. In the example, the system reduces to this system. So in the example, this is the system I obtained from the n part, and this is the only linear relation I have. And because for each linear relation arises because there is a vector on the left kernel of n, right? So each linear relation constraining the dynamics means that there is one redundant equation on this part, right? Because in this case, the linear relation is that the sum of the two equations is 0. So I can get rid of one of them. And you can always do that. You will always find that you can express this set as a square system, meaning that it has as many equations as variables. And then we would expect that each of these sets contains a finite number of points. It doesn't need to be like that, but for more, essentially that's what happens. But the number of values might depend on the parameter values. And we talk of multistationarity when these sets have at least 2 elements, as I said in the beginning. Here in the drawing, in the parameter values giving these 3 points will be a set of parameter values where multistationarity arises, but for this one, no, and for this one, no. Why do we care about multistationarity? Well, we care because in biology, or in the dynamical systems, you care about the property called bistability, meaning you have 2 steady states that are stable. If you have in a system 2 steady states that are stable, it means that under the same conditions, because this is for fixed parameter values, your system can reside in 2 different states, right? And this is sometimes linked to cell decision making in a biochemical context. So deciding whether a system has bistability is an important question in the applications. And well, before deciding whether I have 2 steady states that are stable, I should know whether there are at least 2 steady states, right? So this is like the first question. And it's easier because studying stability is more complex than just studying the number of solutions. So that's the motivation, and that's where we focus on now. And now we enter the first part of the results of this talk, which is on parameter regions of multistationarity. And by that, we mean for what case and C do I have multistationarity? That's the question I want to find, and I want to describe this set in a way that I can use. And sometimes, I mean, you are lucky that you can do almost high school algebra and find the parameter region. Here, this is an example of a network. Now I don't use the X notation because I use like what these proteins are. These are proteins in some bacterial signaling system. This is the reaction. We build a system, and you can reduce solving the system to solving one polynomial equation of degree 3, and then using Sturm sequences, you can characterize when that polynomial will have 3 positive solutions. It will have either 3 or 1, and when it has 2, it's because one of them is degenerate or is double root. And we can do that, and we get, this is the answer, right? This is the parameter region where the system has multistationarity. These A's here are these polynomial expressions on my parameters. So if you expand this polynomial here, it doesn't fit in the screen, right? So these are huge inequalities and polynomials that then you have it, but you don't know what to do with it. What is it telling me biologically? What information can I get out of that? Is it connected? The question I was saying in the beginning. Well, no, it's nice you have it, but no biologist will be happy with that, right? At least, I mean, these other people here, Sawyer and Kotamanshu, they were not happy with my solution that I was happy with. But, well, solutions are complicated. I mean, this is not, I cannot change the solution. That's the solution, right? So that's what it is. But then it turned out that if you, instead of looking at the full parameter region, try to understand the projections of the parameter region. For example, project the parameter region onto the K's, or project them into the C's, or mixed, then you get easier answers that you can interpret, right? And for me, the first reason to look at that was because I could do it, but then I realized that actually the answers are nicer. So now that made me feel that it was actually the right thing to do, to look at these projections. So here I will talk about projections on the case. And there is some related work of other people that you can see here that worked on other types of projections. So for the rest of the talk, I will say that parameter value K enables multistationarity if it can be lifted, right? If it comes from projecting the parameter region down to the case. So that means if there exists a C such that this holds. And then we ask what parameter values K enable multistationarity. And here you can see in this drawing, right? The question of K is about what are the red curves that can be intersected in more than 2 points by the blue lines. So that's the question phrased in a more geometric way. And the answer we gave comes from this result that I don't want to enter into the technical conditions. Essentially, they ask that the trajectories of the system are not unbounded and that there are no boundary steady states. But if they hold, then you can compute a polynomial, which I call pk of x, such that if the polynomial is positive when I evaluate it at the positive ortho for all values of x, then I don't have multistationarity. I have exactly one solution in this set. If that doesn't hold, in addition, I can make the polynomial negative, then I know that for that K, right? So here K is here, there is multistationarity for some C. So K enables multistationarity. This result is simply a Brauer degree theory behind it. It's derived from that. And this polynomial is simply the Jacobian of the system evaluated at the parameterization of the red curves. Right? But you can see this is a quite old result, but it has some nice, yeah.
May I ask? I'm sorry, just to the previous one. Is it obvious from somewhere that this curves, this steady state variety has a parameterization?
No, that's one of the conditions.
Okay, good.
Yeah.
Thank
Yes.
you.
But surprisingly, because when you work with biochemical systems, the degree corresponds to molecules that interact, and proteins there are not 3 proteins at the same time interacting. So usually the degrees we encounter are 1 or 2, and that often implies you can parameterize the variety. So that's a specialty of the setting, of the application setting. But then let's go back to that example that had the very, maybe not very easy to understand parameter region of multistationarity, and I compute the polynomial here. And this is the one, right? This is the pk of x, where I evaluated at the parameterization, as Gleb was asking. And here you see very clear there is only one coefficient that can be negative, all the rest are positive. So you get very easily that if the coefficient here is positive or 0, then this polynomial is only a polynomial with positive coefficient. So it is positive for any values of the x's I put in, as long as they are positive. So then we are in the first case. So the number of a steady state is 1 always. If that's not true, if this is negative, then the question is, okay, can I make the polynomial negative? And here in this case, the answer is yes, because you just let x4 and x5 be equal to t. Then this becomes a polynomial of degree 3 in t, with leading coefficient this number that is negative by the assumption, right? So then you let t be large enough, and this becomes negative. So if k1 is smaller than k3, this coefficient is negative, and the polynomial can attain negative values. Therefore, we are in the second case of the theorem, and I get that there are at least 2 steady states for this k. So we obtain that k enables multistationarity, even only if k1 is smaller than k3. So the projection of that complicated region I showed you before into the case is k is smaller than k3, which I think is quite frustrating and nice at the same time, right? That it was so complicated to see it from the other one. But this theorem gives it to you very easily. But well, here we could work it out. Like, I mean, we had an original problem of understanding the case for which there is a C, such that the system has 2 positive solutions. And this problem has been transformed into another problem that is for which k can my polynomial attain negative values for positive x, right? Apparently, one might think, have we gained anything, right? I mean, this is still a question in semi-algebraic geometry that is still difficult to answer. But here, the trick is that it opens for the use of some polyhedral geometry techniques, which is what I will tell you about. And this, the story is as follows. So if yes. So what I did in the example was to inspect the coefficients, right? That's the easiest thing you can do. Look at the coefficient, right? Look at the sign. And I was lucky that I had a coefficient with negative coefficient that I could, and I could argue that the polynomial actually could be negative, but that doesn't need to be the case. You could have a polynomial with a negative coefficient, like this one, very simple, but it can never be negative because it's a square, right? So knowing that the polynomial has negative coefficients, it's not enough. But there is this nice result that it's well known among people working with these things that says the following. You take the Newton polytope of your polynomial, which is the convex hull of the exponents appearing in the polynomial. And then there is this result that says, sometimes I change and it doesn't change here. Here. It says Maybe let's focus on the last one. If I have a vertex of the Newton polytope, then the polynomial can attain the sign of the coefficient of that corresponding to that vertex. So when I construct the Newton polytope, like here, this is the Newton polytope of my example. The coefficient that could be negative was corresponding to this point because it's exponent 1, 2. This is a vertex. So all the signs that that this coefficient can attain are attained by the polynomial. And that's essentially the trick I used before. The same is true with faces. If you take a face, whole face, and restrict the polynomial there, it means you just remove the monomials that do not have exponents in on the face. If the polynomial restricted to the face attains, for example, a negative sign, then your polynomial will also attain negative sign, right? So the vertex case is a special case of the face case. So that's what worked here. And maybe I just want to say briefly what is the idea of this result. And the idea is that you just take a vector in the outer normal cone of the vertex. So here it would be the cone given by these two lines here. That's what I would have drawn in the iPad if it had worked. But so you have this cone here, you pick any vector there. And then when you pick the vector, you evaluate your polynomial at t to the first component of the vector, t to the second component of the vector, and in general for more. And when you do that, you are guaranteed that, then you get the univariate polynomial, and you're guaranteed that the coefficient of interest becomes the leading coefficient, right? And that's why this works. So very simple and constructive proof. So this approach of finding that pk polynomial, finding the Newton polytope, looking at the vertices, can be used to derive conditions for multistationarity. And it works for really many networks that are realistic. I think if you draw randomly networks, you won't find a parameterization, so then it won't work. But the realistic networks in cell signaling, it works very well. So to move on, just take some time. I will show you very briefly another example. This is a very well-known network for people working on this. It's a network that is very small somehow, or it's small enough such that you feel you should be able to do things, but there are still many unknown questions about the network. So it's a bit of a test case. Whenever you have a method, you test it on this network, which I like to call it the model, like model organisms in biology. That's the model. But here the polynomial looks like this, and there are two types of coefficients that can be negative. This one that is repeated in many places, and this one that only appears in one place. We can apply the theorem. If both of these expressions are positive or 0, we are done. There is only one steady state. It turns out that this one corresponds to some vertex. So then if that one is negative, then I have multistationarity by what I said before. But the P2 that only appeared in one coefficient is not a vertex. It belongs to, it's this blue point in its hexagon phase of Newton polytope. This is the Newton polytope of the polynomial, and the point is there. And now here, we cannot just argue by the sign of the polynomial, of the coefficient. We need to know the value, right? In this example I gave you before, that the polynomial could not be negative. If you increase the coefficient, then it can be negative, right? So the value matters here. And I will just briefly say, because I don't want to spend a lot of time on that, is that by using results from sum of non-negative square decomposition, they're called SONG, and circuit polynomials. Circuit polynomials are polynomials supported that the Newton polytope is a simplex, and there is a point in the middle. Using results from there, this type of polynomials that is very well understood when they can be negative and when they cannot, we could derive conditions for saying when if B1 is positive, that was the one that if it's negative, we are done. And B2 is negative and additionally satisfies some extra condition, then we didn't have multistationarity. And we could also show that actually when this holds, you could also find conditions for which there is multistationarity. So the P2 coefficient can give multistationarity and can give not multistationarity depending on the precise value in relation to the rest of the coefficients. Right? We could also show that what is the boundary between the two regions explicitly, and that the regions in parameter space K, so these projections were connected. So the projection of the multistationarity region and the K is connected. So that's the one slide on that work. It's quite technical somehow, but you can have a look at it. It's published in this journal here. And with that, I will go to the very last part of the talk, which is the very recent work I was mentioning, which is now, we would like to study how many connected components does this region have. It's the basic property, right? You have a topological set that you are interested in. First question you can ask, is it connected? Is how many connected components does it have? And this is a very, I think, difficult question that I've only seen it addressed in one paper, very recent paper of, maybe you recognize Dan Bates here, working in homotopy methods for solving systems of polynomial equations. And that's what they did there. They used some numerical algebra to study when that dual phosphorylation cycle, that's the one I showed you with the hexagonal face, that was that model network. They studied the connectivity of the parameter region. They concluded that it looked like it was connected based on numerical methods. And this connectivity question is something I've been thinking about for a very long time, actually. I think already in 2015, I was telling people in my group, how could we do that? How could we decide whether the region is connected, right? Because it's a very basic mathematical question you want to ask. And then I gave the question, because I give it to everyone in my group, to Mate Telek. He came as a research assistant for a while. Now he's a PhD student here. And then he said, well, I don't know if that's useful, but if we consider essentially this polynomial as a polynomial in the K's and the X, right? If that one, I mean, the anti-image of the negative real line is connected, so the region where the polynomial attains negative value is connected, and it has this technical condition that the closure of this set, you can see here it's open, right? The negative line. It's the same as taking the anti-image of the non-positive line. If that holds, then the parameter region is connected. And so essentially he was saying consider the polynomial, check where it's negative. So in this drawing, it's here. If this is connected and this technical condition holds, then your parameter region is connected. And of course, we ask, did we gain anything again, right? We changed the question to something that has the same flavor, but but we had a good success with the Newton polytope, right? So we thought, let's look at the Newton polytope. There is no way we can look with the coefficients because this is a simple polynomial. The polynomials we encounter are huge. So let's think in terms of the Newton polytope again, right? And then we came up with several results that characterize, depending on the configuration of the exponents, that there will be only one connected component. But the useful one is this one that says that if there is a hyperplane, I think I show you the drawing because it's easier. If there is a hyperplane that puts on one side the points in the Newton polytope that correspond to monomials with negative coefficient, and on the other side, the ones with positive coefficient. And on the hyperplane, you can have everything. It doesn't matter. If that happens, then there is one connected component where this is negative, and that technical condition holds. So that's what we prove. And then let me just briefly say that the idea is essentially very similar to that, moving the points along these paths given by t to the omega. So when the hyperplane does not contain any point, that's any point of the Newton polytope, that's the easiest case. You essentially can show that when you have a point where the polynomial is negative, you multiply it component-wise by t2, a vector in the outer normal cone. T to the normal vector to the hyperplane separating the point, right? Then these points, when you increase the t, g remains negative there. So if you start at the point where the g is negative, then you move them along this path, g remains negative. And then the idea is that if you have 2 points, you can choose this w such that in the end, the 2 paths meet. So you connect them. So that's the idea behind, in the case where the separating hyperplane does not contain points of the Newton polytope. If it contains, then you need to do some extra things to reduce it to this case, essentially. So that was the theorem, and now you can see putting the dots together. Here, that we had the theorem saying if we can find a g such that if this holds, the parameter region is connected, and then we have a theorem to decide what this holds, right? So if we put it together, what we need to do is to consider this g function, and this g function now does not depend on the existence of parametrization. So now we got rid of that condition. We still need the boundary steady states and boundness of trajectories, but we don't need the parametrization anymore because now we vary the case. So we have more flexibility, essentially, that's the idea. But we find the g, which you can always find, it's easy. You find the Newton polytope, you see if it is separating hyperplane, that's a linear optimization problem. If there is, then your parameter region is connected. And we tested it in that beautiful network I had in the beginning with a very complicated parameter region. It's connected, good to know. I wouldn't have known how to do it from the original equations. The dual phosphorylation cycle that was part of that numerical study that suggested it was connected, it's connected. We verified that now theoretically. And then we tested many other networks. We are still testing others, but essentially this table is more to illustrate that the method works very well. Like here we have a G polynomial with almost 20,000 terms, right? And in less than 5 minutes, we can decide that the parameter region is connected. And no way you can find it at the descriptors of the parameter region, right? So we are quite happy about this method, I would say. And well, I think that's all I wanted to talk about. So I would say thank you for your attention.
Thank you very much, Elisenda. So we have some time for quick questions, and we will have more time for more detailed questions after the breakout room discussion. So if there are some short questions from now, please just unmute yourself and ask, or you can ask in the chat.
I have a question.
Yeah, Thomas, please.
Your results, do they hold for general polynomial right-hand side, or do you need mass action kinetics?
Any. Yeah, you need the conditions that you control what happens with the trajectories. Somehow they are, it's called dissipative, right? They eventually enter a compact set, and you need no boundary steady states. So this is what you need. But it's not relying that it is mass action. It could be any kinetics that, or any polynomial system of all the equations that satisfy these two properties.
Yeah. Thank you.
That was about all the results, or about the last one, about connectivity?
About the last one is only this, and the first, the previous one where we construct a polynomial, you need the parametrization. well, you need the parameterization if you want to find a parameter region in the case. If you just want to answer, is there multistationarity or not, you don't need it, because when you have the K-free, you can always parameterize the set K comma X, where X is a steady state for K. So that one you can always parameterize. That's the thing. But if you fix the K, then you need to make sure you can do that. That's the thing.
Okay, any other quick questions for now?
I just had,
Willem?
oh, sure. So I just had a question about the, if you had any examples where the set parameters for multistationarity was not connected.
Not yet. Not yet.
But
But
do you have a
somehow,
theorem?
if we don't find the separating hyperplane, we cannot conclude that it's not right. So we need other ways to verify. So the theorem is only for, is it connected? Right? You can answer yes, but if you don't find the separating hyperplane, you don't know. So I mean, I'm sure you can construct like a non-realistic network, because this is arbitrary polynomial systems essentially, but one that comes from a system that one believes is makes sense. We don't have it yet, but as I said, it is still work in progress.
Your pictures at the beginning suggested that the steady state variety is zero-dimensional for all choices of K. Is that a requirement, or does it come out of the theory, or what's the status of this?
We cannot say that it's zero-dimensional for all choices parameter values, but yeah. So, but the theorem will tell you if there is, like, if that polynomial is has only positive signs, you know there is one steady state for each K and C. So in that case, you know, right? But when it says that there are at least two, you cannot conclude that there are a finite number. No.
Pictures were in 2D, and if you have two polynomials in 2D, you do not have much choice besides having a zero-dimensional thing. I think in higher dimensions, the pictures would look different.
Somehow we have so much, I mean, the way the polynomials are constructed, I have the feeling if the red equations are non-linearly dependent, then I don't know of any example, I think, or why, where the variety has always the wrong dimension, or like this set, and it's not because there are linear dependencies. I mean, you can find one K where the dimension is wrong, but for all Ks and Cs. But that's an open question that to understand when that happens. Yeah.
Okay, so I think it's a good time to go to breakout rooms for like 10 minutes, and then we can get back and ask further questions. I have a couple of philosophical questions on the matter.
I'm worried now.